Welcome back to this unit on thermodynamics, and we will go through today about the criteria for spontaneous processes, and we will introduce entropy and Gibbs free energy. Just to recap what we have learned in last class, and so basically we have learned that reaction enthalpy or enthalpy of reaction or heat of reaction is total energy of the enthalpy of the product minus total enthalpy of reactants. So, if I just plot in two axes, x axis is your reaction coordinate, if this is your reactants, and say here you have products, corresponding energy level is this. So, if this is H P is the total enthalpy of the product and H R is the total enthalpy of the reactants. This is H in y axis, x axis is reaction coordinator. So, in this case we are writing H R is total enthalpy of reactants and HPR is total enthalpy of products. Then in this case the reaction enthalpy of reaction delta R H is given by this difference, and this is product minus reactants is a negative value. So, this is exothermic reaction. Similarly, if I have the other case where I have again reactants and products reaction coordinate. In case I have product reactants at low level, so H R and products at higher level H P. So, the difference is this. So, this difference is the product total enthalpy. So, this in this case this is the enthalpy of reaction is greater than 0. So, this is a endothermic reaction, endothermic, and this is a exothermic reaction. Now, as we explained that this we cannot always we need to keep the reactants and products in a standard state for comparing the values. So, we defined that standard heat of reaction or enthalpy of reaction, where all the products and reactants are at their standard state, is given by summation of the enthalpies of products minus summation of enthalpies of reactants. So, this is standard molar enthalpy of the products and this is standard molar enthalpy of the reactant. So, if you multiply it by number of moles, which are the stoichiometric coefficients in the balanced reaction, this gives you the standard heat of reaction, where both the reactants and products in their standard state and a particular temperature T. Now, we also showed later on that you can express this in terms of the heat of formation of products minus standard heat of formation for reactants. And these values, this heat of formation for products and reactants are available in literature, and some are there in your book, as I have taken from NCERT book. You can see this table. In this case, you can see those the heat of formation, standard molar enthalpy of formation of heat of formation is at 298 K or 25 degree centigrade is given for several substances. Now, sometimes for gaseous reaction, if you do not have the values for this enthalpy of formation, you can get the standard enthalpy of reaction from bond enthalpies of reactants minus total bond enthalpies, this summation bond enthalpies of products. In this case, it is reactants minus products, and how it is arrived we have talked, we have discussed in last class, and this is for applicable for gaseous reactions. So, if you know the bond enthalpies for compounds, we can get delta R H naught, standard enthalpy of reactions, and some of the values are available in literature, and this is some are shown given in your book. So, we later on we continued on discussion, and in this case, as I said that this we are not talking about number of moles in the reaction, it is just balance equation. So, this is the extensive quantity, and the balance equation stoichiometric coefficients are number of moles, and if you reverse the reaction, the value it will be negative of that. Then we continued and discussed other reactions like heat of formation, standard heat of formation at a particular temperature. Then we talked about standard heat of transition, and which are many types like fusion, vaporization, sublimation, and we talked about combustion, we talked about atomization, we talked about solution, we talked about reaction enthalpy for ionization. So, ionization enthalpy. We also talked about electron gain enthalpy for electron gain, and all these are for 1 mole of substance. Okay. So, these are all intensive quantities, because here we are making sure that we are dealing with 1 mole of compound, either it is formation, combustion, vaporization, all this is related to 1 mole of substance. Then we also talked about thermochemical equation, which is nothing but the actual reaction plus the reaction enthalpy of reaction, standard enthalpy of reaction values. Then we talked about Hess's law, and we talked about Born-Haber cycle. This we based, the basis of these two was that delta H naught or delta H is an state function. So, it depends or it does not depend on the path. So, these are basically what we discussed in last two classes. Now, we go back and look at the first law again, first law of thermodynamics, which says that when one form of energy is converted to another, the total energy is conserved. That is the first law of thermodynamics. So, we have said that delta U for isolated system is 0 and delta U for closed system Q plus W, and we discussed what are these term means closed system. Now, what it means that if system is losing some energy, say for example, if system is losing some 10 joule of energy. So, Q system if I write as minus 10 joule because it is losing some energy, then surroundings if I write Q surroundings, it will absorb the same amount of it. So, it will be plus 10 joule. So, total Q it will be 0. So, basically no energy is created or destroyed here, only 10 joule of energy got transferred to the surroundings. This is what exactly the first law says. It does not says, first law does not says about the followings. Whether this transfer I just mentioned, whether the energy transfer will happen at all. If happen, then which direction it will happen? If it at all happen, how long it will happen? Again, if it is happen, then how fast or what is the rate at which this energy transfer will happen. So, basically these are 4 questions is not answered by first law. So, what we will do today's discussion will able to answer us the first 3 questions, but this is the rate at which energy transfer or reaction happened is not part of thermodynamics. It is part of kinetics, okay, which is not subject of this topic of this unit. What we know? We know that what do we know? We know that some process happens, processes happen spontaneously. For example, I'll just put it a bullet point, like I have spreading of perfume. So, I have sprayed some perfume one corner of the room. What will happen? You will get the smell after some time from the other parts of the room as well. So, spreading of perfume. This is just example some spontaneous processes. Gas expand into vacuum. If I release a gas into vacuum, gas will immediately expand and occupy the total volume. hot object, if I keep a hot object in a surrounding which has lower temperature, then the object will cool down and will take the temperature. So, if I have a pen which I is a hot pen, like the temperature is high, if we keep here, then that heat it will basically give up some energy and it will take up the temperature of outside. So, this happens automatically. A weight falls from a height. If I keep the pen up, then leave it, it will automatically or spontaneously fall below. If I ignite a fuel on ignition, a fuel burns spontaneously. So, these are the some example, I can name many other examples, but these are the some examples where this spontaneous process happened. And if you think of the reverse process, like if I have a smell, if I have a like in this room has already have some perfume spreaded, it is not happen that automatically the perfume will come back and concentrate on one of the corner of this room. That is not happen. Like if I have a gas occupied in a container, then it will spontaneously not happen that some gas will come to one part of the container and make the other part vacuum. So, that will not happen. Like if I keep this pen at the same temperature outside, it will never happen that some heat will come and suddenly heat this pen and make it as a higher temperature. So, that is not happen. So, those are the process we are talking about non-spontaneous happen. Like if this pen I have kept here, it automatically goes up, it will not happen. So, some examples we just gave for spontaneous. So, what is spontaneous process? And this process happens irreversibly, because as I said the reverse process will not happen spontaneously. So, these spontaneous processes are irreversible process. So, what is spontaneity then? We are talking about spontaneous, this word for spontaneous. So, a spontaneous process means, so spontaneous that the process has a tendency, or we can call potential, to occur without any assistance from external agency. So, without any spontaneous process will happen naturally, automatically, like without any assistance from external agency. What do we mean by external? The assistance from external energy, this term assistance from external energy means we are talking about some work having to be done, like some that the surroundings should do some work to bring it about. So, this help or assistance we are talking about means that without any work having to be done to bring these changes or bring this process, bring this happen. So, the non-spontaneous process we talked about, the reverse reactions or reverse processes, we just gave example where we require to the process cannot happen, here it happens or it has a tendency to happen, but non-spontaneous process will not happen. So, will not happen without the help from external energy, without assistance from external, which means if I have to lift the pen from it to a height, obviously I have to do some work on the surroundings. If I have to like reduce the volume of this is a volume of the system, if I have to reduce, then I have to push the cylinder inside to bring it to new position. So, that which means I have to do some work on the system. So, basically non-spontaneous process like decrease in volume, in this case I have to apply some external assistance to do that. So, spontaneous process is an irreversible process which can be, I can also write spontaneous process is an irreversible process which can only be reversed by doing work. That is, reverse is the non-spontaneous process. So, reverse process of spontaneous process is non-spontaneous process. So, now you should be knowing what is a spontaneous process and what is a non-spontaneous process. Now, so what should be the criteria for spontaneous process or spontaneity? So, criteria for spontaneous processes. If I go back and look at the some example like the temperature, I have kept this pen which has a higher temperature, I kept it here. After some time the temperature will decrease and will occupy or it will take the temperature of the surroundings, which mean in this case energy is decreasing. So, this example we gave here, energy is decreasing, energy decreasing. Now, if I have the pen which I leaving it going down, again energy is decreasing. There are some spontaneous chemical reactions which are exothermic. Some example we can give. This is one of the examples of spontaneous reactions which is exothermic. So, in this case also energy goes down. So, the examples we have seen here till now, these 3 examples, which means which shows that the spontaneous processes reduces energy. But does it always true? The spontaneous processes will decrease the energy. We will give few more examples. So, in these examples we have seen the spontaneous processes decrease energy. That is for these 3 examples we are seen, but that is true for always. We will see, we will look at other examples. Now, this is also that this energy is decreasing for what? This is decreasing for the system. If I consider the plane as a system which was at higher temperature, then I keep it here, it will dissipate heat, come to the temperature of surroundings. Then in this case, the system, the plane is giving away some heat, but the surroundings is gaining some energy as a heat, because the energy cannot be created or destroyed, which means that in the spontaneous process, if somebody loses energy, the surroundings is gaining energy. So, energy is not that the universe is losing some energy, that is not happening, but the system is losing some energy in these examples, but we will look at some other example as well. For example, let me take a slab, say iron slab, and we have a two sides. One side I have at 60 degree centigrade and the other side I have at 20 degree centigrade. There was a insulating wall or non-adiabatic wall in between. I have this surrounded by adiabatic wall. So, that is my initial state. Now, if I remove this, the barrier thermal insulator, then what will happen? There will be exchange of energy in from heat from this to the other side, and I will have the entire slab as 40 degree. That is my final state. Now, because it is surrounded by adiabatic wall, no energy is getting lost to the surroundings, but in this case this part is losing energy and this part is gaining same amount of energy. So, in this process I can always argue that this is a spontaneous process where heat is getting transformed from 60 degree to 20 degree centigrade, but in this process one part is losing energy spontaneously, but the other part is also gaining energy spontaneously. So, if you think this is a system, then I will say system is gaining energy spontaneously for a spontaneous process, which means that I cannot only talk about energy as a criteria for, I cannot talk about only energy decrease of energy or energy change as a criteria for spontaneity. So, that is not, I cannot tell that now. I can give other examples where we are not changing the energy at all. For example, if I have a ideal gas, kept it here in again two sides, I have kept it this in a constant temperature bath at T, both are at T, this is ideal gas. This side is vacuum. So, initial state, this side pressure is 0 vacuum and this side some volume of gas is there V 1 and this side is V 2. Now, what will happen if I remove the barrier in between? You will have the ideal gas will occupy the volume of total volume V 1 V 2 and temperature will remain same. This is the final state. What is the change in our, what is the energy change in this process? Again this, because this is a expansion against 0 pressure or volume. So, W should be 0. I am talking about ideal gas, constant temperature. So, del U is 0. So, obviously, Q should be 0, which means there is no change in heat, or there is no exchange of energy as a heat happens in this process. But what happened? Spontaneously the gas expand from initial volume V 1 to final volume V 1 plus V 2. So, in this case no energy change, no heat energy change is involved, but the gas expand spontaneously. So, again energy cannot be a energy change, or heat energy change cannot be a criteria for spontaneity. I will give you one more example where I have a gas, two different gas separated by a boundary. One side I have this gas, blue gas, violet gas, and another side I have red gas molecules. Now, if I remove this, my initial state at temperature T. Now, if I remove the barrier, again the, now what will happen? You will get the gas all over, both the gas in the entire volume. So, that will be my final state. So, what happened? It is the gases are mixing spontaneously. If I consider these two are ideal gases, then there will be no interaction between them. So, which means there will be no change of energy related to this. So, again in this case also we are saying mixing is mixing of ideal gases are spontaneous, or is spontaneous, and in this case also the energy decrease of energy is not a criteria of spontaneity. You cannot just link to spontaneity this condition. So, then what is happening? If you look at this, we can also look at some reactions, chemical reactions where the reaction is endothermic. For example, I can note down one example where this is a spontaneous reaction, but it is a endothermic reaction. So, in this case energy is actually going up, the system's energy is actually going up, but the reaction is spontaneous. Again we go back and say that decrease of energy is not, or energy alone cannot be a criteria for spontaneity. Then obviously, what is the criteria for spontaneity? That question will come. What is the criteria? If you go back and look these processes, and we will see what is happening. See, in this case, if I talk about the spreading of perfume, what is happening? I have kept a perfume in a, spray the perfume in a corner, then spontaneously what is happening, that it is, the matter is getting dispersed in all over the room. So, basically it is becoming more random. I have this hot object, I have said this hot pen, I kept it here, and it will dissipate heat energy to the surroundings. What is happening? The energy in this case is getting dispersed to the maximum possible volume, and if I consider the system plus the surroundings, it is giving getting more, the energy is getting more dispersed or most disordered or most randomization of the energy. If I talk about this two example, in this case the particles, constituent particles were moving at a faster speed. If I take this as a gas containing at 60 degree centigrade, the gas molecules will move faster, and in this case the gas molecule will be slower. But when you remove the barrier, basically the energy will dissipate and randomize, and you get a mixture of these two. In this case, gas matter, it was restricted in this volume, and as soon as I remove this barrier, the gas particle will dispersed and occupy the same volume. So, basically from a concentrated scenario, it is becoming more random or more chaotic. So, what we are now getting idea that in this all these spontaneous processes, what is happening, either the matter or energy is getting dispersed throughout the system, and the system or the system plus surroundings together is getting more random is becoming, whether in terms of matter or in terms of energy. So, basically what we can tell that natural tendency or spontaneous tendency is to get disperse or randomize or say disordered, become disorder. So, that is the, or become chaotic, whatever you call. So, basically these are the terms we can use interchangeably, that natural tendency is that the matter or the energies will spontaneously get randomized or become disordered or spread as much as possible, basically disperse. Space mean we are talking about disperse. We just give a just for non technical examples, like if you have a kid at home, like if you have a small kid 1 or 2 years old, then what will happen if you just give a bucket of toy or a toys, give it to him or her, small baby. Now, after some time you will find that the baby has scattered all the toys, so dispersed and randomized. So, she does not know or he does not know what to do. It is not that reverse, that if those toys are scattered throughout the room, that small baby will come and collect and put it there in one place, which is naturally does not happen. For example, if I go into class which has 3 sections, like, and each section has 100 strength approximately. So, total strength is 300. Each section 1 has 100, section 2 100, section 3. Now, first day, and I have basically 3 places, left side, right side and the back of the classroom. And when I enter in the first class, I ask this question, tell me which section you belong to in one of the parts, and then there I will find that the students from section 1, section 2, section 3 will occupy the entire room, entire classroom. It is not that the section 1 student, they do not know at the, I am talking about the first day when they do not know each other, there is no interaction between them. Once they know each other, there will be interaction between them, they will probably try to sit next to each other. But in the first class, when they do not know each other, there is no interaction between them. So, they will disperse. Okay. So, you will have a classroom which has a random population of section 1, 2, 3. So, this is just a natural example that mixing or getting dispersed or randomization is a a natural tendency, and we can explain this by statistically by probability, but this random states or random mixing is probably higher probability than where you have one section is one part and other section other part, but this explaining this from a statistical point of view is not part of this unit. So, we know now that we have a natural tendency to disperse or randomize or. So, now what we have to do? We have to quantify this randomness. So, basically what we will do, we will quantify this randomness. Now, we introduce in this time, we introduce a thermodynamic parameter entropy, symbol is S, capital S. This is basically the quantity which represents the randomness in the system or surroundings. So, if the value of S goes up, we know that the randomness, extent of randomness goes up, and if the value of S goes down, then the extent of randomness go down. So, for any, now we can write for any spontaneous process, the value of entropy of system plus entropy of surroundings will increase. Or if I write delta S, change in entropy of the system plus change in entropy of surroundings would be a positive value for a spontaneous processes. And if I make a isolated system where the surroundings is not interactive to the system, for isolated system only delta S system will be positive. So, this is what we are concluding or inferring from the experience we have noticed till now. And when we summarize a experimental observations or natural phenomena in terms of a equation or in terms of any statement, we call that as a law. Law is nothing but it is a summary of the experimentally observed or naturally observed phenomena, and we call this as second law of thermodynamics. Where we say that for any spontaneous processes, the entropy of the universe, system plus surroundings will go up. So, always the because all the time spontaneous, there are several spontaneous processes happening, that means the entropy of the universe is always increasing because the spontaneous processes are happening. Just a few things about entropy. Entropy is extensive quantity. If you double the quantity of mass, it will double value of the double. It is state function, and so delta S is independent of path. Now, how do you mathematically get this value of entropy? So, we will try to now get we will try. The value of S from some relations. Now, what we have seen that if we add some heat energy as a heat, the molecules move faster. If you are talking about gas, they move faster. If you are solid, they will start vibrating with a higher oscillation amplitude towards the mean position. So, basically we see that when you add some energy as a heat, entropy goes up. So, when we talked about this pen which has a higher temperature, we keep it here, the heat disappears, heat dissipate, and in this case the entropy of the surroundings which is gaining the energy as a heat will increase, but the entropy of this pen for which it is losing some energy on cooling, it will basically entropy will come down. Now, we know that Q only appears during a process, means if I bring a system and surroundings or two objects of different temperature, then heat exchange happen, and the magnitude of heat exchange we call Q. If there is no process going on, we do not bring this quantity Q, which means Q should be related to change in entropy. As I explained, when this having higher temperature kept at in the surroundings, it is losing energy. That means, the change in entropy is negative for the pen and change of entropy is positive for the surroundings. So, basically if Q is positive, if I add some energy as a heat, delta S will be positive for either system or surroundings. So, if I go back and look at the example which I have given earlier, see if I have two sides and this is surrounded by adiabatic wall. This is at temperature T1 and this is at temperature T2. If I think this is a system, this is surroundings, then from experience we know if T1 is greater than T2, then some heat will, the energy will flow as heat from system to surroundings. So, Q will be negative and delta S system will be less than 0 and Q of surroundings higher and delta S surroundings will be higher. Now, we know that Q for system or Q for system plus Q for surroundings is 0. That we know from first law of thermodynamics, we explained, I just explained the beginning of today's lecture itself. So, if delta is only related to Q, then obviously the decrease of entropy is exactly matched by the increase in the entropy. So, if I think that delta S is only related to, if delta is only related to Q, then in this process of transfer which is happening spontaneously, delta S will be 0, total delta S for system plus surroundings which is not the criteria. We know that to a spontaneous process happen, delta S total, which is for system plus surroundings, has to be positive number. So, delta S for system, delta per surroundings has to be positive number. Now, to if this has to be positive, then delta S system, which is a negative quantity, the magnitude of delta S system has to be lower than the delta S surroundings. I am talking about this particular example. Okay. Delta S system is negative and delta S surrounding is positive. So, if the magnitude of the positive number is higher than the magnitude of the negative number, we will land up delta total greater than 0. Now, how can I, what is the difference here? The temperature is difference. Now, you can look at that. If I look at the temperature, and if we can think that delta S is inversely proportional to temperature, then obviously this was at lower temperature to begin with. So, the entropy gain will be higher for surroundings and the entropy loss for the system will be, the magnitude of the entropy loss for the system will be lower, because T 1 is greater than T 2. And how long it will happen? As long as the moment T 1 becomes T 2, then there will be no heat transfer, there will be no process. So, you will get a reach a equilibrium. So, we also know that if I add some amount of energy as a heat to a system we have a lower temperature, then the increase of entropy will be of higher amount compared to if I add the same amount of heat energy at a higher temperature, which means that we are talking about that entropy change is inversely related to the temperature. So, we have found earlier that a entropy change of entropy is related to Q. If Q is higher, delta S should be higher. So, somewhat directly related to delta is directly related to Q, and now we found that delta is actually inversely related to Q. So, with these two in mind, we will define mathematically delta S for the system delta S as Q reversible by T. Q reversible is the change in energy transferred to system reversibly. Please keep this mind, reversibly, this is important, and T is temperature in Kelvin. Please also keep this mind, this is not a centigrade, Fahrenheit, something not, it is always in Kelvin. So, Q reversible is the energy transferred to the system reversibly, and T is the temperature in Kelvin. We will just talk about few examples where entropy increases. We just look at some examples and see whether what happens to entropy for the system. Like we will take a liquid, say water is becoming a gas, a vapor. What happened in this case? Delta S for system, I am talking about liquid as a system. So, delta S system is positive. Now, if you talk about liquid becoming solid, in this case delta S system is less than 0, negative. Now, if I talk about water as a liquid, then you know that liquid to vapor or water to water vapor or water to ice may happen spontaneously, depend on the temperature here. If I talk about say 25 degree centigrade, say 125 degree centigrade, then water will become water vapor spontaneously. If I talk about minus 25 degree centigrade, then water will become ice spontaneously. Now, in this case the entropy of water is increasing, and in this case entropy of water is decreasing. Now, water to ice is a endothermic process, and water to ice is a exothermic process, and water to vaporization is a endothermic process. Now, in this case, because exothermic process, some amount of heat is coming out to the surroundings. So, though in this case the system's entropy is going down, but the surroundings entropy is increasing even more in magnitude. So, the total entropy for change for system plus surroundings is positive. Similarly, in this case this is endothermic process. So, surroundings is losing some heat to the system. So, in this case the entropy change, entropy increase for system is higher compared to decrease in entropy of the surroundings. So, basically the temperature which determines which is the direction for spontaneous processes in this case. There are other examples like we talk about increasing the temperature of a solid from say 10 degree K to 120 K. At lower temperature the constituent particle will move and oscillate about their equilibrium position at a lower extent, whereas a higher temperature it will move and oscillate to their mean position as a higher extent. So, it will become disorder more, which means entropy will increase. So, delta S would be positive for the system in this case. Example, if we talk about say one bicarbonate, sodium bicarbonate solid is dissociated So, because of solid to gas formation, here also entropy increases, entropy is positive. There could be some other example as well. Now, in this case we are talking about spontaneity delta S system plus delta S surroundings greater than 0 for a spontaneous process. Now, we cannot always look for surroundings, because some cases the system is a open system or closed system. So, we will try to get some parameter which will be only focusing for system. So, that now we can determine the spontaneity based on a property only for system, and that we will talk about in the next class. We will not next class I will try to focus on only the system and try to get some property which will determine the spontaneous process based on its value only of the system.